And good afternoon, everyone. May I first thanks the International Association of Catalysis Societies and the ICC Committee for inviting me here. I'd like to give a special thanks to our Asia-Pacific Associations of Catalysis Societies for nominating my name as a keynote here. I'm particularly happy to be in this preparation of heterogeneous catalyst sessions. So what do you think of improving performance of heterogeneous catalysts? I bet we will think of like the way to get maximize the dispersion of the active site by modifying the preparation methods or changing the support or adding some promoters. My story today that I'm going to talk with you is nothing relating to those. It's pretty much something unconventional. It's new to me. It's probably new to you guys as well. I'm very inspired by the award talk by Professor Yuli when he said that electricity may have something to do to boost up the catalyst performance, and this is something we are being investigating in my group for about 3 to 4 years as well. I'm Joongjai PANPRANOT, and I'm from Faculty of Engineering, Chulalongkorn University. Chulalongkorn University is located in the center of Bangkok, Thailand. It's about 10,000 kilometers from Bangkok to Lyon. So if any of you happen to visit Bangkok, you can just connect me or try to reach me anytime. Very welcome. Here's the outline of my talk today. I'm going to introduce you to some special catalytic system with these negatively charged metal nanoparticles. They're catalysts that we are not pre-prepared before use. We just going to activate them during the system. And they have high capability, so much that they have super power for the reduction of any various carbon sources. I put CO2 in my the title of the talk just to draw some attention, but actually they can be able to reduce any of those carbon sources all the way to crystalline solid carbon. And yeah, I'll show you some of the previous study, that already available in the literature. And then the rest is mostly just our application of this in-situ negatively charged system. This is the overview of the talk. It will be start with the CO2 electrochemical system, and I shift a little bit to work with the reduction of the MEA CO2 capture system. We do some scaling up of our process, and then we obtain the nanocrystalline carbon as our products. We study some effects of the types of the metals, and then also the synthesis route, modify them a little bit. They also be able to convert liquid oxygenates or the biomass-derived compound, again, all the way into nanocrystalline carbon products. And the special that is that everything has been done at room temperature, ambient pressure, with just a little bit of electricity. So let's go to the first one. This is the system that I'm talking about. The catalysts were made, we call it in situ electrochemically induced. I use a little bit of electricity to create this negatively charged metal nanoparticles. And they have a very, super catalytic power that be able to reduce all those carbon sources into gravitic carbon products. And a lot of them. You can ask me later how much I get. And yeah, all at room temperature, ambient pressure. Let me give you some definition of these negatively charged metal nanoparticles. It's going to be metal nanoparticles with some excess electrons. And these electrons not bound to the metal atoms. So they be just being accumulated on the surface and they're free to move. And this stage of the metal nanoparticles that are super active, I tell you in a little bit. In the field of heterogeneous catalysts, we may be familiar with electron transfer from support to the metal, right? Where metal support interaction, that's pretty much some conventional. So like in this case, we have platinum on the left side, have platinum on titanium dioxide, and then they have some second elements to the titanium dioxide, and they be able to boost up the oxygen reduction reaction activity by 10 times increase of the mass activity of the platinum in that case, and that was in 2019 in Nature Catalysis. And just last year, Professor Sung Kim from Suwon, Korea, he reported what so-called negatively charged platinum nanoparticles that supported on dititanium oxide electride. The electride crystal, you have a stream of electrons in the anionic layers. So when you have platinum precursors, and the platinum still undergoes a reduction, and you still have the stream of electrons coming. So you end up having some excess electrons on that platinum nanoparticles. And there, the catalyst activity in oxygen reduction reaction increased by 31 times. It's 89 times increase in specific activity in oxygen reduction reaction. And the stability is quite nice. That's the work found in the literature. Actually, the electride materials pioneered by Professor Hideo Hosono from Tokyo Tech. And here they show the ruthenium on the electride support, although they didn't call it as a negatively charged ruthenium, but electron transfer from electride support to ruthenium. It even changed the ammonia synthesis, in which well-known, like the nitrogen dissociation has been known as a rate determining steps. There's no longer rate determining step on this ruthenium catalyst, like just a surface reaction between adsorbed nitrogen and hydrogens. There's also some other techniques that you can create negatively charged metal clusters. Like in this, on the right side, we have ruthenium clusters placed under molten sodium chloride. There's a lot of solvated electrons, so you end up having negatively charged ruthenium. And again, this ruthenium exhibit like a very superior nitrogen dissociation activity. We have more recent work have shown application of this excess surface accumulate excess electrons on the metals in some organic synthesis. Or on the right side, it showed that these surface electrons keep copper from being oxidized even under ambient air. Okay, talking about the surface accumulated electrons, we may see some similar phenomena, not exactly the same, but that's like for the surface plasmon effect on the metal particles. When you're excited by electrons beam, you can end up have the localized surface plasmon resonance. And this on the left is gold nanoparticles. And what's special here is that they exhibit, CO disproportionation reaction at room temperature. So you can create CO dissociation, you get carbon on that. On the right side is the plasmonic silver. And in this case, alcohols are turned into graphene oxides. Okay. So there are some kind of negatively charged metal nanoparticles that been around, recently, that show a superior catalyst performance. And in our case, this is one of our first study way back in about 2020, where we have performed carbon dioxide reduction reaction under electrochemical system. But it turned out that we produce a lot of graphene carbon as a products. This is a bismuth particles deposited on tin foil. And yeah, the first question, maybe you just, maybe just some carbon from your electrolytes. No, we have checked, there's no change in the form of our electrolyte. And we have a little bit of the CO gaseous products, but mainly the major products here is the nanographene if we look at the structure. And if we calculate the Faraday efficiency, it's like way beyond, I put number 10,000 here, but it's actually way beyond that. So it's not really electrochemical pathway here for the carbon formation. We use a small amount of electricity to, actually the work actually started off with some serendipity, but we are learning, a little bit to get to know more on it. This is the graphene that we got from this. It has about size of 2-3 nanometers. So like a small graphene pieces are joining together. It's like all over our electrodes. That's what we first observed. And how do I prove that it's come from CO2? Later on we prove more, but at that time, if we don't have any CO2 gases in the system, if we just try to reduce our electrolyte, there's no carbon formation, so almost no reaction at all. We have tried with different metals here. That one was bismuth, cobalt, zinc, nickel, tin, lead, silver. We be able to produce such reduction of the carbon dioxide into graphitic carbon materials. It's except gold that we have tried under different conditions and we not be able to make the same results. And what's the difference here? Gold are less oxyphilic than the others. So we are kind of thinking that there may be some clues, from this, the presence of the oxide layers on these metal particles. And we actually we look up in the literature, we found some, we found some, this is the before ours. It's a work from the group from Australia. I think they use cerium nanoparticles. And then under CO2 reduction reaction, they also end up having a lot of carbon as a products. That's a cerium nanoparticle in liquid metal system. And they propose that the reduction of the thin oxide layers, that like maybe something to do with this pathway, but there's no further explanation from there. But what we are, usually what happened, actually this everybody might know, working with the electrocatalysis, you have deposited metal. And in this case, we have a highly conductive substrate. So like when you apply negative potential, the oxide, the presence of the oxide will be reduced, the metal oxide reduced, and they can undergo something called nanocrystallings. That's why we see change in morphology, etc., right? But if you just have a small amount of oxide, and if you make it well stabilized, there was some circumstance that we can have excess electrons deposit, on our metal nanoparticles that form. That's why I say in situ electrochemically induced negatively charged metal nanoparticles. Our DFT results kind of support this hypothesis that the anion silver clusters are actually well stabilized under our electrolyte system, while the neutral ones are destabilized, even under the gaseous intermediates, like CO intermediates. Okay, there's something to do with the oxide, so we have a further investigate, like, so how much the oxide we need, or how can we, is there any point where we can even improve the further? So we treat this is silver nanoparticle. We do electrode deposit first on the copper, and then do some treatment. So there's some cases where we can enhance this carbon, production. And there's also some case that we shift the way the reaction into towards CO gases instead of making carbon. So now that we actually learn more, that is what's way. So if you have too much of the oxide, actually this won't work. If you have too little, it's also won't work, something like that. And now we try to, with our collaborators from Osaka University, we try to look in the pathway for CO2 to carbon. So people have looked it up already. And that's it. There are thermodynamically feasible, either via COH or CSO. So CO dissociation, into carbon is not feasible via the electrochemical pathway. Interestingly, that we found that if you have like a lot of CO absorbed, or actually at least 2 CO molecules is absorbed on silver, especially the negatively charged silver, this CO disproportionation reaction or the Buddha reactions is feasible now at room temperature under reaction. So you can have the CCO for now. And can we have a lot of CO around silver? This is from the literature that DFT studies show that the anionic silver 20 cluster can take up to 19 molecules of CO. Actually, you can have a lot of CO around this negatively charged silver. And this is from our own work. See that we can make the carbon grow even longer chain with the help of this solvation effects from the salt that we use. So now the reaction seems feasible now. Spontaneity of the reaction has been just recently proven that it's possible here. And that's when we work with the aqueous CO2 system, and we just have CO2 gaseous dissolved in our electrolyte. And we're thinking that the mass transfer probably not so good. We want to have more CO2 in that system. So we shift our, we try to modify our system a little bit. Now it's just look at like this, just a simple single compartment electrolysis cell with, we have MEA as to capture CO2. So CO2 will be chemisorbed in the form of MEaCOO minus or the carbamate species. And we can even replace the expensive ionic liquid. Previously in the previous work we used BMIM, BF4. Now we use ammonium sulfate salts. So now the carbon sources are just CO2 or MEA or the carbamate species. And yeah, if you look in the literature, there's people trying to do direct conversion of MEaCO2 as well. And we can get CO or formate depending on the electrodes that you use. And the electrolyte usually CO2 in MEA with some salt. But in our particular system and with our negatively charged silver, we can produce, there's a lot of graphitic carbon quantum dots formation, from this reaction. And again, the Friday, I can't calculate the Friday efficiency. I can, but like this give me the unrealistic number. So it's kind of a proof that it's probably not the electrochemical pathway. We did have a small amount of a gaseous product like CO and hydrogen, but with the Friday efficiency like less than 1%. There's no liquid product as we confirmed from like NMR. This is what we see from the reaction. What we do here, we have a electrochemical cell loading with MEA, and then we load CO2 in there, put our electrode, and apply the potential, which is quite low. We applied, I think, minus 1.3 volt versus silver chlorine here. And after performing a 90-minute reactions that we call first run cycle 1. And then we can even reuse the electrolyte. We replace with a new electrode. We purge more CO2 to capture more CO2. That's cycle 2, and then run again. And we do this for 10 cycles. And end up, we have like the color of the electrolyte change from the clear solution to brownish color. And it exhibits a very strong fluorescence properties, which is one indicator that we have carbon quantum dots in the solution. It's also proved by the peak, a strong absorption peak in UV-vis spectroscopy at around 290 nanometers, which is the presence of the carbon quantum dots. And also PL results. Okay, no liquid products and no, change in the structure. Okay, here I want you to pay particular attention to the current density. If we have the carbon deposit like in any normal case where it deactivates the catalyst, your current density will decrease. I mean, you would say you will see some deactivation. But here, the more of carbon we produce, the higher current density. And how is that possibly occurs? Just trying to explain by the on the top figure that we have electrons coming to create the state of these electrons on the silver, and the actual electrons will flow out to reduce carbon dioxide, and we draw more electrons. So that's why our current density increase and increase, I mean higher and higher. And that's the one we use with CO2 in the presence of CO2. Without CO2, if we just do this with MEA, even for 10 cycles, it's negligible current density that we being observed. It's actually just obvious from the TEM images. The presence of the graphitic carbon quantum dots with a size around 3 to 5 nanometers can be seen just from TEM images. They are actually, if we have high concentration, they can merge and in the form of the graphene sheet, let's say. That's our carbon in the electrolytes. And we look at take the electrodes and look at the electrodes. We see like a thick carbon films as well here. It's starting from a cycle 1 to a cycle 10. This is after cycle 10 without CO2, so there's almost no carbon deposit on that case. On this CO2 system, we have like a thick carbon film, and it shows the graphitic nature, like from the Raman, and also we see some linear C2 carbon species as well, which seems to be our intermediates into this graphitic carbon quantum dots formation. And we take like a closer look to these carbon films on the electrodes. We just take the carbon out and do diffraction at the pure carbon area. They show very nice crystalline structure that match perfectly with graphene. And there's also some lattice spacing that match with progressive diamond. So the carbon products on the electrodes are having sp2, sp3 hybrid carbon, but they are very, very well crystalline in nature. It's been called something like progressive graphite to diamond. We really make diamond here. We take a look like if we between bismuth surface and silver surface. From bismuth, I showed you previously, we can apply bismuth in our MEA CO2 system as well. We see small graphene joined together on the right. On the left, I'm not sure. It's we see some distortion and some stacking of the small graphene. That's how they shift towards the diamond. Okay. The system is simple enough to be scaled up. We scale up our system from 50 milliliters to just 2 liters size system with a stack of an electrode cell. And yeah, we be able to obtain a lot of carbon quantum dots in the solution and also on our electrodes. And after repeated use, so making more and more carbon, we can separate our carbon product out by just simple dialysis and then freeze drying. And the amount of carbon, okay, if you ask me the yield, it's about 10% yield, not so much, but that's really from carbon dioxide, you know. So we got 10% or 10% yield, that's from the first cycle, I think, carbon quantum dots, and then separate them out. And I already apply them. They already found applications like can put just a little bit to make it to enhance the strength as a cement concrete strength enhancer. We can use in batteries. I already applied them in a different type of application. So if you're interested in my CO2 derived carbon, you can just contact me. Okay, next we have, if it's work with CO2, it work with CO2 MEA system. It's going to work with other liquid oxygenates as well. And now the carbon source is only liquid oxygenates. the salt is ammonium sulfate. And here we have the acetic acid, formic acid, something like that. And to prove our concept further, the existence of the negatively charged silver, it's something like, are you sure to have it? We have the deposited particle before, and we think that they have some oxide layers that we need to reduce them to create this negatively charged light. So if that's the case, it would work with when we just don't have the pre-electron deposit particle. We just have the bare copper foil. We just add a little bit of silver cations. We should be able to get the same thing if the concept is correct. And yeah, this is when we have electron deposited silver, and then we apply electricity to induce the negatively charged silver. And yeah, we be able to make like a solid graphene sheet. Like we see a trace amount of the carbon quantum dots on our electrodes, and we see the structure of the carbon. And here is on another route where we modify the synthesis system, where we don't need to like pre-deposit the metal. We just have the copper foil, and we add a small amount, ultra small amount of silver in the solution, apply electricity, small amount as well, and as end up we be able to create the same thing. So the carbon that we obtain are like pretty much the same as the previous route. So this is kind of to prove, I mean, for us as well, that this is there's something there that doing this reaction. It's not all the case that we get like positive result. What if we have excess amount of oxides? How to do that? If like in the previous work that we try to treat to make even more oxide. First we thought we want more active sites, something like that. But turn out that if we have excess amount of oxides, probably this doesn't help and even worsen the reaction towards carbon. Or if we apply too high potential, what happened? It's going to face, it's going to force the negative bias of the metal nanoparticles under this nanocrystalline system. There's also worsen, no reaction towards the carbon. If we have insufficient amount of oxides, we also didn't make it all the way to the sp2, sp3 carbon. We see some linear acetylene carbons as well. And yeah, this work with acetic acid, it worked with other types of the liquid oxygenates. So when we learned that we can do in situ electrodeposition and reduction. In this work, we try to vary the amount of the silver that we put. It just turned out that we can just, if we have too little, like on the top one, that's very little, maybe too less silver to make this happen. But if you have starting to have enough silver, yeah, you even end up having some nanodiamond here. This is the effect of the reaction times. It actually, the diamond occur even at the beginning, 15 minutes. If we look here at the figure, we will see, if we try to see here, this is we see that the silver actually deposited first, and then we have the carbon formation. And then afterward, we have like another silver coming, cover it. Okay. Now we try to look further what happened with that the C2 radicals that we seen from our Raman spectrum, that it's a part of our product as well. In this experiment, we generate C2 radicals by electrooxidation of calcium carbide, and then apply our negatively charged into our negatively charged system. And here I missed the pictures, but actually we end up having graphitic carbon from C2 radicals, both in the electrolytes and also on the electrodes. And I'm talking about the transformation of the graphene structure towards sp2, sp3. If that's the case, it should work with our commercial graphene. How about trying a commercial graphene quantum dots? So now I purchased commercial graphene quantum dots. It has this Raman structure like this, the Raman pattern like this. So in this case, there's no other carbon sources. We just have our negatively charged system. We add a little bit of the graphene quantum dot that we purchased after, and then after apply electricity, and wait for some times. And here is the Raman of the graphene quantum dot. It did change a lot. So that's possible that there are transformation. Actually, I would tell you that depend on the size of the graphene quantum dots, and there's still some many parameters here, but we see some possibility here to manipulate the sp2, sp3 hybridization of the carbon under this nanoscale system. Do you still have time? I'm sure. Okay, and this is just our proposed idea from the liquid oxygenase reduced into C2 radical is for grow like linear satellite carbon chains from graphene quantum dots, and on silver in particular, it's that can induce sp2, sp3 hybrid carbon formation. And yeah, it works with biomass-derived compounds. Well, usually if you want to convert this biomass-derived compound into graphitic carbon, you need maybe 1,000 degrees or 2,000 degrees to make it graphitic. But here we convert these sugars into graphitic carbon at room temperature. So in conclusion, I believe I show you this. There exists the highly efficient supercatalytic power of this negatively charged the metal nanoparticle with accumulated electrons on it that can do this reaction and even transformation sp2, sp3. So in a broader context, we believe that this synthesis could shift from the energy-intensive bulky process towards low-energy nanocatalytic system for the carbon allotrope synthesis. It's possible to apply, into synthesis of other nanocrystalline materials as well, or maybe even catalyze any inert chemical reactions under ambient conditions. There's a lot of possibility here. Thank you. Oh, yes. This is a startup company that we extend from this work with my former student. He's here as well. And yeah, thank you.